Chemistry 20. This is our fourth lesson in the Quantities in Chemical Reactions unit. This is Displacement Reactions. In this lesson, we will learn about single displacement and double displacement reactions, and we will learn how to predict the products of both chemical reactions. Single displacement reactions. This is a reaction that occurs when an element in a compound is replaced by another element. In our chemical reaction, we can see that A, our lone element, is going to replace C, the element in the compound. As a result, we will form the products A, D, and C is now the element by itself. To recap, we have switched A with C in the compound to form new products. Consider the following. In a single displacement reaction, we have to remember that cations, positively charged atoms, will only replace cations in the compound. And the opposite is true. Negatively charged atoms, anions, will only replace anions in the compound. For example, sodium has a charge of +1. That is a cation. Therefore, it is going to replace the cation in the compound. Lithium also has a positive charge. It is a cation. Therefore, sodium will replace lithium in this chemical reaction. Predicting single displacement reactions. Step number 1. Displace the element in the compound with the lone element. Remember, again, cations only displace cations, and anions will only displace anions. Step number 2, use the zero-sum rule, aka the swap and drop method, to determine the product. And don't forget diatomic atoms if they are displaced. Number 3, determine the state of all reactants and products. And finally, number 4, balance chemical equation. Examples number 1. Predict the products, the state of each species, and balance the following chemical reactions. Pause the video and attempt this example. For the first chemical reaction, we have the following answer. First up, we have to determine the copper has a charge of +2. Therefore, it is a cation. It will replace the cation in the compound. It is going to displace silver. We are then going to form the compound CuCO3. To do that, we have to use zero-sum rule. Copper has a charge of +2, and CO3 has a charge of -2. So when we swap and drop and then simplify the charges, we are left with CuCO3. And then finally, silver was displaced. It is not a diatomic atom, so it is just silver by itself. We have copper, which is a metal, a solid by itself. And we also have Ag2CO3, which is an ionic compound at room temperature. Therefore, it is also a solid. CuCO3, again, an ionic compound at room temperature, is a solid. And then finally, silver is a metal by itself. it is a solid. Finally, we just have to balance the chemical equation. In our second chemical reaction, we have the following answer. Now this example is slightly different. Chlorine, Cl2, has a charge of -1. It is an anion. Therefore, it is going to replace the anion in the compound. It is going to replace iodine, I. We are then going to form the product, NaCl. Na has a charge of +1. Cl has a charge of -1. When we swap and drop the charges, we are left with NaCl. We are displacing iodine, which is a diatomic, so we are forming I2. The question says, chlorine gas is bubbled in a solution of sodium iodide. So we know that Cl2 is a gas and NaI is aqueous because it's a solution. This tells me that the entire reaction is occurring in water. Therefore, we have to consider if our products are soluble in water. And if we look at the solubility guidelines, NaCl is soluble in water, therefore its state is aqueous. And finally, iodine, I2 by itself, is a solid. We then just have to balance the chemical equation. For our third chemical equation, we have the following answer. Sodium is a cation, therefore it is going to displace Mg, which is the cation in the compound. We are then going to form products, Na2O. We are using the zero-sum rule to find the ratio of the compound because Na has a charge of +1 and oxygen has a charge of 2-. Therefore, when we swap and drop our charges, we are left with Na2O. And then finally, magnesium was displaced. It is a metal by itself, so it will be a solid. In the question, they are providing states of both reactants, so solid sodium and aqueous magnesium oxide. So therefore, it gets physical state of aqueous. Again, we know this reaction is occurring in water, so therefore we have to consider if our products will be aqueous as well. So if we look up on the solubility guidelines, we will see that Na2O is also soluble in water, so therefore it will be aqueous. In our final chemical reaction, we have the answer. So we are reacting iodine, I2, which is an anion, so it is going to displace the anion in the compound. It will displace sulfur. So we will then form the compound CaI2. To do that, we have to use the zero-sum rule. Calcium has a charge 2+, iodine has a charge of -1. When we swap and drop the charges, we are left with CaI2. We are then displacing sulfur, and sulfur by itself is S8. To consider the state of all species in the chemical equation, iodine itself is a solid, and we have calcium sulfide, which is an ionic compound at room temperature, so therefore it will be a solid. And then finally, our products, we have calcium iodide, which is, again, ionic compound at room temperature, so it will be a solid. And sulfur, S8 by itself, is again a solid. Please note that there was no indication that this reaction occurred in water. This is why none of our substances will be aqueous. Finally, once we've concluded the physical state of each reactant and product, we just have to balance the chemical equation. Double displacement reactions. These reactions involve the exchange of cations between two ionic compounds, and this reaction usually occurs in water. If we look at our example chemical equation, we are going to exchange the cation ions between AB and CD. Therefore, A is going to take the place of C, and C will take the place of A. As a result, we will be left with the products CD and AD. Consider the following. A precipitate is an insoluble solid that is formed by a chemical reaction of two soluble compounds in water. What is important to note for double displacement reactions is that we must form a precipitate in a double displacement reaction, or this reaction will not occur. In order to determine if a precipitate is formed, we have to use solubility guidelines. Predicting double displacement reactions. Step number 1, switch the cations of the two reactants to form the products of the chemical reaction. Number 2, using the solubility rules, determine if one of the products will form a precipitate. If no precipitate is formed and both products are aqueous, no reaction will occur. Number 3, use the zero-sum rule to determine the products. And then finally, number 4, balance the chemical equation. Examples number 2. Predict the products, the state of each species, and balance chemical equations when the following solutions are mixed. Please note that all of these examples, each of the reactants is a solution, therefore their states will be aqueous. Pause the video and attempt this example. For the first chemical reaction, we have the following answer. Step number 1, we have to exchange the cations between the two compounds. So we are going to switch Fe and Na. That results in the following products. Fe2 brackets SO4 bracket 3. If we check solubility guidelines, this product will be soluble in water. It is aqueous. And our remaining product is NaCl, which is also aqueous. Since we did not form a precipitate in this chemical reaction, there is no reaction that will occur, so we can say no reaction. We have not balanced the chemical equation because there's no need. No reaction is occurring. In our second chemical reaction, we have the following answer. Step number 1, we have to switch the cations. We are going to switch Ag and K. That will form the products KNO2. We are forming KNO2 because K has a positive 1 charge and NO2 has a negative 1 charge. So when we swap and drop, we are left again with KNO2. And our resulting product, we have Ag, which has a charge of +1, and PO4, which has a charge of -3. So when we swap and drop the charges, we are left with Ag3, PO4. If we check the solubility guidelines, KNO2 is aqueous. Ag3, PO4 will form a precipitate, it will be a solid. Therefore, this chemical reaction will occur. Finally, we just have to balance the chemical equation. In our last chemical reaction, we have the following answer. Step number 1, we have to exchange the two cations. We will be switching Ca and Na. Forming the products, CaCO3 Calcium has a charge 2 plus, and CO3 has a charge of 2 minus. So when we swap and drop and then simplify the charges, we are left with Ca, CO3. Our remaining product is NaF. Sodium has a charge of 1 plus, and fluorine has a charge of 1 minus. So when we swap and drop the charges, we are left with NaF. If we check the solubility guidelines, Ca, CO3 is a solid in water. It will form a precipitate. And then finally, NaF will be soluble in water. Its physical state will be aqueous. That represents that this chemical reaction will occur because we are forming a precipitate. Finally, we just have to balance the chemical equation. Neutralization reactions. This is a double displacement reaction involving an acid and a base. Products of a neutralization reaction are predicted using the same methods as a double displacement reaction. The only exception is that there is no formation of a precipitate. Neutralization reactions will occur because of the formation of water. This is the exception compared to other double displacement reactions. Formation of water allows this chemical reaction to occur. The general equation for a neutralization reaction is the following. An acid plus a base forms an ionic compound, also known as a salt, plus water. If we look at the chemical reaction below, we are seeing an acid, HNO3, plus a base, NaOH, is forming an ionic compound, NaNO3, and water. At times, neutralization reactions can be difficult to balance. To make them easier to balance, we can change H2O to HOH. That allows us to balance hydrogen, H, here, and with the acid, and also allows us to balance the polyatomic ion OH, which is represented here and represented here. Moving forward, we will learn about combustion reactions.